Welcome to Chapter 6 and Section 6.1. In the previous chapters, in Chapter 4, we introduced the concept of a vector space. We looked at how we define a vector space, look at the properties of what makes the vector space. In Chapter 5, we looked at the inner products of a vector space and how we can perform operations upon vector spaces. In Chapter 6, we're looking at going between different vector spaces. So we're going to be transforming one vector space into another by establishing relationships or connections between them. So in this section, 6.1, we're going to define a linear transformation and look at just a whole bunch of examples of what that looks like. So a linear transformation is a function from a vector space V to another vector space W, written T from V to W, such that T of V1 plus V2, so if you take two vectors that are added together and you transform that result, that is equal to T of V1 plus T of V2. So the transformation of the sum is equal to the sum of the transformations. What we say is that T, the transformation, respects addition. And T of K times V1, where K is a real number or a constant, is equal to K times T of V1. So in other words, the transformation of the scalar multiple is equal to the scalar multiple times the transformation. And this means that T respects scalar multiplication. Okay, and this is for all vectors in V and for all real numbers K. So to show that a transformation is a linear transformation, we need to prove that these two properties will hold. For a given transformation, we need to show that it respects addition and it respects scalar multiplication. If it satisfies both of these conditions, then it is what we call a linear transformation. So let's take a look at our first example here. So we're going, V is the vector space M2 of R, so all 2 by 2 matrices with real number inputs, and W is just R, is just the set of real numbers. We define T to be going from V to W, so we're transforming 2 by 2 matrices into real numbers. That's what's happening in the transformation. And the specific relationship, how we're doing that, is defined here. So if we take a matrix A, B, C, D, when we transform that matrix, we turn it into a real number defined as A plus D. Okay, so we take the first component and the fourth component, add them together. That is how we're defining this specific transformation in this problem. Okay, notationally, I should note, when you see something like this with like the colon equals, that usually means that we're setting equal. So we're setting this transformation of A, B, C, D equal to A plus D. So we'll do that a lot when we establish transformations, especially just in the beginning of the sections here. So to show that T is a linear transformation, we need to check that it respects addition. So we're going to need to establish a couple of vectors in the introductory vector space, in the first vector space, V, and then see if we can show that this relationship holds true. So we're going to take T of, let's see, with A, B, C, D, I need two vectors. So let's go ahead and do A1, B1, C1, D1 plus A2, B2, C2, D2. Let's go ahead and combine. We can combine component by component here. So this is going to be A1 plus A2 B1 plus B2, C1 plus C2, D1 plus D2. And now that we have transformation of a 2 by 2 matrix, we can go ahead and perform the transformation. So we take A plus D, so that's the 1, 1 component plus the 2, 2 component. So that's A1 plus A2 plus D1 plus D2. Now that we have performed the transformation, now let's see what we can do with these. So these are all just scalars now. We have A1, A2, D1, and D2. Let's rearrange a little bit. Let's regroup the 1s together and the 2s together. So A1 and D1 are grouped together, and A2 and D2 are grouped together. But this, A1 plus D1, this would be the transformed value of A1, B1, C1, D1, which is this first matrix. And this would be the transformed value for the second matrix. So we can go ahead and revert back. So undo the transformation step just on these individuals. So A1 plus D1 would be T of A1, B1, C1, D1, plus this is the transformation of A2, B2, C2, D2. So we have that the transformation of the sum is equal to the sum of the transformation. So this one does check out. It does respect addition. Now we need to check that it respects scalar multiplication. So we need to establish a scalar here. So we're going to let k be a real number. So we get T of k times A, B, C, D. So we're going to take transformation of the scalar times a vector. So this is Ka, Kb, Kc, and Kd. Right? So we can multiply that in. Now we have a 2 by 2 matrix, so we can perform the transformation now. So that's going to be Ka plus Kd, right? The 1, 1 plus the 2, 2. Now we're working with the scalars here. We can factor out the k. We're left with k times a plus d. And again, a plus d is the transformation of the original matrix. So this is k times transformation of a, b, c, d. So once again, we have transformation of k times the vector is k times the transformation of the vector. So this does respect scalar multiplication. So we can say, therefore, T is a linear transformation. So this transformation gives us a relationship between 2 by 2 matrices and real numbers. And we've shown here that because the transformation respects addition and it respects scalar multiplication, it is a linear transformation. Let's take a look at another one. So because we're moving between so many different types of vector spaces, these problems can all look very different from each other, but the overarching pattern will repeat every time. The overarching process of testing for respect of addition and scalar multiplication will remain the same. So for this example, we're going from v to w, so from p4 to p3. So these are polynomials of degree 4 or less being transformed into polynomials of degree 3 or less via the transformation of p of x equal to p prime of x. So basically, we're using the derivative as a transformation here. So we're turning a 4th degree polynomial or less into a 3rd degree or less by taking its derivative, right? And if you think about it, right, if you take the derivative of x to the 4th, that's 4x cubed, so the power does go down by 1. So hopefully, intuitively, this should make sense that it should work. So let's check it. So we're going to check that it respects addition. So we're going to let p of x and q of x be elements of V. Okay, so the input vector space. So they're going to be 4th degree polynomials or less. So T of P of x plus Q of x the transformation is going to differentiate this function. So we're going to take the derivative of P of x plus Q of x. And we know from the properties of derivatives that you can differentiate across sums and differences like this. So this would be the same thing as P prime of x plus Q prime of x. And P prime, that is the transformation of P, and Q prime would be the transformation of Q. So this is transformation of P of x plus transformation of Q of x. So transformation of P plus Q is transformation of P plus transformation of Q. So it does respect addition. Now to respect scalar multiplication, so we're going to let k be a real number. Transformation of k times P of x. Again, we have the same type of situation here. So this is the derivative of k times P of x. But you can pull constants out of derivatives. That's a property that we know from calculus. So this is k times P prime of x. And P prime of x is the transformation of P of x. So because it respects addition and it respects scalar multiplication, we again then can say therefore T is linear. So it is a linear transformation. For our next example, something a little different. Here we're going between generic arbitrary n by n matrices to real numbers. And the transformation that we're using is T of A equals determinant of A. So we're using the determinant to transform matrices into numbers, which is what the determinant does. The question is, does the determinant form a linear transformation? Does it respect addition and scalar multiplication? So let's check for whether or not it respects addition. So we're going to let A and B be elements of V. So these will be n by n matrices. So we'll take T of A plus B, transform that. That would be the determinant of A plus B. In order for this to respect addition, we would have to get out T of A plus T of B like this, which means we would have to be able to split this determinant. However, we know from back in chapter 3, that determinants do not split across sums. So determinant of a plus b is not equal to determinant of a plus determinant of b. If you want like just a quick counterexample of that, take the matrices like 1, 0, 0, 0 and 0, 0, 0, 1, like that. Determinant of a would be 0, determinant of b is 0, but if you add the two together, determinant of that one is 1, so not equal. But this as a general rule is not true, meaning that we cannot split the determinants, which means we cannot get t of a plus t of b, which means that this transformation does not respect addition. So t does not respect addition. So it is not a linear transformation. And we don't even need to check whether it respects scalar multiplication or not, because if it fails 1, then that's an automatic no. Right? It's an automatic no. It is not a linear transformation because it has to satisfy both in order to be a linear transformation. So one interesting fact about linear transformations that can also help us as we're going through this process, if you were to transform the 0 vector in V, so that's this notation, so that's like the 0 vector for the vector space V. So the input vector space, if you transform its 0 vector, that will give you the 0 vector of W for the output vector space for any linear transformation. Okay, so for any linear transformation, if you transform the 0 vector of the inputs, you will get the 0 vector of the outputs. Okay, so like in our past examples, right, you know, the 2 by 2 0 matrix would have transformed into the number 0. The polynomial of degree 4 or less, 0, would be transformed into 0. And we'll see some additional examples of that going forward as well. The justification for this, so we know that if the transformation is linear, then the 0 vector, we could go ahead and split this into 2 copies of itself, right? Because 0 plus 0 is 0. Because the transformation is linear, we can actually split these across the sum. So we have transformation of 0 equals transformation of 0 plus transformation of 0. If we subtract one of these off from each side, what you have left here is nothing. So you have 0, but it's not just 0, because when you're dealing with transformations, after it's been transformed, you are now in W. You are now in the output vector space. So this would be the 0 vector in W over here. And on this side, you subtracted 1 away. So you're left with transformation of the 0 vector in V. And that is exactly the relationship that we have defined. So let's take a look at an example involving this. So we have transformation going from P2 of R to M2 of R via this transformation. So we're turning polynomials of degree 2 or less into 2 by 2 matrices using this specific relationship. Is T linear? Well, if we try out the 0 vector, so the 0 vector for a polynomial is just the number 0. That would give us, so A is 0, B is 0, and C is 0. So that gives us 0, -1, 0, 0. But what we should be getting is the zero vector in M2, which would be the 2 by 2 zero matrix. Right? And this is not that because of this -1 here. And that -1 will always be there. So the zero vector in V did not transform into the zero vector in W. Thus, T is not linear. So there are some cases where showing that the transformation is not linear can be simplified simply by observing the relationship between the zero vectors. Does the zero vector of the input vector space transform into the zero vector of the output vector space? Now, just because it does work doesn't guarantee that it's a linear transformation. We'd still need to check that it respects addition and respects scalar multiplication, but it can be used effectively to contradict a linear transformation. Okay? So, or I should say a nonlinear transformation. Okay? So it's kind of like with the zero vector check when we were testing subspaces back in chapter 4. Right, the zero vector, if it's not there, can be very useful in showing that it's not a subspace, but if it is there, you still have to test it. Same thing here. If the zero vector transforms appropriately, we still have to test and verify that it is a linear transformation. But in this case, the zero vector doesn't even transform properly, so it's not linear. If we take a look at this next example, we're transforming from R2 to P2. So we're transforming ordered pairs into polynomials of degree 2 or less via this relationship. Is T linear? You can check and see that T of 0, 0 gives us 0. So it does transform the zero vector appropriately, which means that we still have to check and see if it respects addition and scalar multiplication. So respects addition. So we're going to let AB and CD be elements of R2. T of AB plus CD so we go ahead and add them together. So that's going to be A plus C and B plus D, component by component there. Transform. Okay, so we go first component is A plus C, right? Second component is B plus D. So just replace all of those in there. So that's going to be A plus C plus B plus D minus 2 times A plus C x squared. And now that we have all of these factors here, so A plus C are just a sum of scalars, so we can split those up. We have B plus D minus 2A plus C, so all times x squared, right? So this is, B plus D minus 2A minus 2C, all times x squared, like that. We can go ahead and regroup together and then distribute the x squared to those different pairings. So we end up getting A plus B minus 2A x squared plus C plus D minus 2C x squared. Which gives us transformation of AB plus transformation of CD. So this transformation does respect addition. So now we let K be a real number. Take transformation of K times AB. So that's Ka and Kb. Transform it, so that's going to be Ka plus Kb minus 2Ka times x squared. There's a common factor of k in here that you can factor out to the front, but then that factor of k can also get factored with this factor of k. So we can just pull a k all the way out to the front. So this is k times a plus b minus 2ax squared. And that is k times the transformation of a and b. So that we do have that it respects scalar multiplication as well. So since the transformation respects addition and respects scalar multiplication, we can say, therefore, T is a linear transformation. All right. Let's look at something a little bit different here. So we have a transformation going from R2 to P2. So kind of like the one that we just had. Assume that T is linear. So this is different. We're not showing that it's linear. We're assuming that it's linear. If we know that transforming the point 1, 0 gives us 3x minus 5, and transforming the point 0, 1 gives us 7x squared plus 2x plus 1, they want us to compute the transformation of negative 3, 2. Now, the point negative 3, 2, we can break that up into different pieces. So it's kind of like the idea of breaking it component by component, putting it in terms of like the standard basis, if you will. We know that this is the same thing as negative 3, 0 plus 0, 2, which is the same thing as negative 3 times 1, 0 plus 2 times 0, 1, like that. And the reason I want to do that, of course, is because I want to put it in terms of 1, 0 and 0, 1, the things that we already know. Now, because we're assuming that T is linear, that means that it does respect addition and it does respect scalar multiplication. So we can split it across the addition and we can pull out the constants. So we get negative 3 times T of 1, 0 plus 2 times T of 0, 1. And these two things we know. Those are what we're given in the problem. So we get negative 3 times 3x minus 5 plus 2 times 7x squared plus 2x plus 1. Distribute, combine like terms. We get 14x squared minus 5x plus 17. So we were able to find the transformation of this vector by putting it in terms of the other two vectors that we already knew. Okay, and this property is going to hold true for more than just ordered pairs and polynomials like this. In the remark we have right here, if this set of vectors v1 through vn is a basis for v, and the values of the transformations of that basis are given, then we can compute the transformation of a vector v for any vector v in the vector space. So remember what it means to be a basis. If this set of vectors is a basis for v, that means that you can create any vector in v using some linear combination of these vectors, right? Any vector at all can be created using those. And if we already know how all of those transform, then we can do exactly what we just did. We can take the transformation of the basis, rewrite our original vector in terms of the basis, and then transform it that way. Okay, and that's kind of what this is talking about. So if we know that this forms a basis, that means that this vector can be rewritten in terms of these, and we can transform those because we already know those values. That allows us to transform any vector v in the vector space. All right. Next up, we have a different type of transformation that we're going to be looking at a little more extensively throughout the chapter. So fix an M by N matrix A. We can view A as a linear transformation from Rn to Rm as follows. So define transformation from Rn to Rm as T of x equal to A times x. Okay, or in the shorthand, T of x is A times x there. So a matrix A can be used as a transformation for a vector x, an n by 1 vector. This is kind of like when we're finding the solution to a system of equations, right? So setting it up in that context, we can use it to transform vectors that are n-dimensional into vectors that are m-dimensional. So just to verify that this does form a linear transformation, let's check that it respects addition. So we're going to let x1 and x2 be elements of Rn. And T of x1 plus x2. We transform by multiplying by a matrix, so that's A times x1 plus x2. And we know with matrix multiplication, it is distributive as long as you keep the matrix on the same side. So as long as A stays on the left, you can distribute it. So that's AX1 plus AX2. And this would be the transformation of x1 and x2 individually. So that's T of x1 plus T of x2. So it does respect addition. For scalar multiplication, so we let k be a real number. We take T of k times x. So that's A times kx. And again, the scalar can move throughout the matrix multiplication. So k can go ahead and move to the front. And then that becomes the transformation of x. So it does respect scalar multiplication as well. So it turns out that this matrix A, when performing this matrix multiplication, can be used as a linear transformation to transform a vector from Rn to a vector in Rm. So for example, show that the transformation from R3 to R2 given by this relationship is a linear transformation. So we have 3x minus z, negative x plus 2y plus 4z. So we have a three-dimensional vector turned into, so there's 1 and there's 2, a two-dimensional vector. So we can write T of x equals, if we set this up as a matrix, so we're going from R3 to R2, so this is an M by N matrix where M is the output and N is the input vector space. So this will be a 2 by 3 matrix with the first vector here having 3, 0, -1, right? That's x, y, z right there. Second vector, -1, 2, 4, times the vector x, y, z. Right, where this vector here, that's our vector x. And you can see, right, 3, 0, -1. If we go row to column, we get 3x, 0y, -z. If we go row to column, we get -x plus 2y plus 4z. This matrix multiplication perfectly gives us this relationship, right? You input the x, y, z here, you get out this vector by running this matrix multiplication. So this does have the proper form, and it does give us the same type of result. So we recognize T has the same form as above. So T of x equals A times x. And we already proved that this form provides a linear transformation. So which means T is linear. This type of transformation, unsurprisingly, is called the matrix transformation, which is what will always be used for transforming Rn into Rm. So if we're going between two vector spaces of real numbers, so between ordered, double ordered pairs and ordered triples, like ordered fourth powers and fifth powers, things like that, we will always use the matrix transformation to go between them, and it works the most effectively. So we will see more examples with the matrix transformation in the upcoming sections, but that brings us to the end of section 6.1. That is our introduction into the concept of a linear transformation going between two vector spaces and showing that the transformation respects addition and respects scalar multiplication. And we'll see more of the nuances, more of the applications and the effects that we can do with linear transformations in the rest of chapter 6.